All right, test 1 2 1 2. This is a test for those on the live stream. We should be streaming out video to the internet, and we've got our fancy wireless mics here ready to also provide the audio. Can I have a little bit of feedback from IRC? Is that streaming? That's going out. That's streaming. Why hasn't it changed over yet? Preview, public view. There we go. Oh, I hear audio here. Audio is good. We have from MyBit. Thanks, Mr. N. And Piranha32, who is a regular here, has also said it works. All right, great. So it looks like we're almost ready to go. So actually, one little thing, if you have your, who's brought a laptop and wants to try out some SDR? You guys have SDRs hooked up? Yep. So as you might imagine, and this will be something that I guess will persist through upcoming meetups too, since we are using this new damn fangled wireless technology. Where's the other little? Oh yeah, we've got this lapel mic as well. These are obviously transmitting analog FM audio. If you want to bring along your SDR and try to find the frequency that we're using, and I don't know, maybe jam or play your own thing into it, there are actually two channels that this thing uses. So if we're not using one, you could easily get in on the other. I can't remember whether there's a pilot tone or something like that, but there's fun to be had. So we're giving you advance inspiration. So we'll kick it off then. Neil, how about I set you up with the lapel mic just so we can say we tried it out. Testing, 1 2 3. Okay, so now we're both mic'd up. Do you want to give us a level test, Neil?
Testing, 1 2 3.
Go again.
Testing, 1 2 3.
All right then, let's just hit record here. It's recording, and then we'll also hit record over here. All right, Neil, why don't you take it away?
Okay, good evening, everyone. My name is Neil. Thank you very much for coming tonight. I'd like to welcome you to the 16th monthly Cyberspectrum meetup. This event series serves as a forum for the exchange of knowledge and ideas related to software-defined radio, and generally aims to get people interested and excited about the applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome, no matter what your software or hardware background. At each meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. The event here tonight is being sponsored by Bastille Networks and is being hosted by Noisebridge. Our first speaker will be myself. I will present the second session in an ongoing series of short GNU Radio tutorials. This time, we'll look at how to construct an FM radio receiver and decode the RDS digital subcarrier. This will include an explanation of some of the concepts behind commercial FM radio and RDS, receiving mono FM, building the GR-RDS out of tree module, and using GR-RDS to receive stereo FM and RDS. We'll also talk about building GQRX and using it to receive FM. Our second speaker will be Dr. Shandor Silvashi from Bastille Networks. He will give a presentation titled Understanding the LTE Physical Layer. LTE is an incredible yet complex cellular networking standard. Shandor will break down and explain how an LTE signal is constructed. He will also do a live demo of the demodulation and decoding of a local carrier. Dr. Shandor is a principal architect at Bastille Networks and earned his PhD from Vanderbilt University in 2014. His team came in first place at both the 2013 DARPA Spectrum Challenge as well as the 2013 Virginia Tech SDR Challenge. After the two speakers, we'll run an interactive install and setup fest with the group. We would like to open up the forum to those who wish to get set up with SDR, hardware or software, and we hope that you have brought your equipment with you. As a group, we can examine and debug the steps required to get you up and running. This could include setting up an app, or fixing an out-of-tree module, or addressing an environment issue that you have in your system. All meetup presentations will be recorded and posted online, as well as streamed live on YouTube. The videos for all the previous Cyberspectrum events have already been posted. We have set up a channel on IRC on Freenode called #Cyberspectrum as a way for people to remotely watching the live stream to contact the local group here with any comments or questions, as well as to alert us to any audio-visual problems. Future meetup locations will alternate every month between here at Noisebridge and the Edis Research Office in Santa Clara. However, breaking with tradition a little bit, the next meetup will tentatively be held here at Noisebridge again on Wednesday, July 13th. Further details will be posted on the meetup page about 1 or 2 weeks prior to the event, so please tune in, pun intended, for all the details, including a list of speakers and presentation topics. Looking ahead further beyond July, we may tentatively run a Cyberspectrum at DEF CON in Las Vegas.
That was supposed to be a secret, Neil.
We got to get people psyched up.
Yeah, there you go. All right, well, we've got some exciting stuff ahead.
I'll skip the other secrets. There are more. I'll skip them. As always, if you'd like to present something or if you have any ideas about future topics, then please let us know. We would like to thank all of our speakers tonight for their efforts and enthusiasm, and we would especially like to thank both Bastille Networks for providing complimentary pizza and soda, and Noisebridge for providing this space and hosting the meetup. We would ask that you help support Noisebridge by leaving something in the donation bucket by the entrance. We would like to announce that we are interested in collaborating with the community to bring the Cyberspectrum meetups to other locations. Our colleague Pamela O'Shea has launched a meetup in Melbourne, Australia. They've had 4 successful events so far, with a 5th one scheduled in a few weeks. We would invite anyone with an interest in starting a local meetup to contact us. There's a lot of SDR activity in the Boston, New York, Washington, D.C., and Los Angeles areas, and also in many places outside the U.S., such as Canada, Europe, including Germany and France, formerly the UK, India, and elsewhere. So these locations may be good candidates for hosting regular meetups. We look forward to hearing from somebody soon. Before we get started with our first speaker, I'd like to introduce someone to make an announcement. We encourage members in the community to make announcements, and today I'd like to introduce Andy Leek, who'd like to address the group and make an announcement. Andy.
Thank you, Neil. Here's Andy.
Thank you, Neil. My name's Andy. I am a volunteer with a wilderness search and rescue group called BAMRU. That means Bay Area Mountain Search and Rescue Group. We are associated with the San Mateo Sheriff's Office, and we're called in to search for missing people all over Northern California in wilderness areas from Mount Shasta up to the Oregon border. I'm here with a teammate of mine tonight, Kevin Morey, and we are very interested in exploring uses of SDR in search and rescue. Over the past few years, we have recovered a number of people whose cell phones were still actually active when we found them. And we believe that if we could have some sort of a capability to do direction finding on a cell phone signal, that we could very potentially reduce the amount of time that it takes to locate a missing person out in the wilderness. Neither Kevin or I are experts in SDR by any means, so we're here tonight asking for mentors. We understand the hardware and software world very well, but it would really help us if we could partner with somebody who could give us some coaching and some advice. So if this sounds like something that's interesting to you, please come and chat with us during the break.
Thank you. Okay, so with that, we'll get started in just 5 minutes and start the tutorial. If any of you have laptops and SDRs with you, feel free to get those out and power them up and follow along. We'll start, I'll go through the slides in a minute. Just get your systems up and ready and feel free to follow along or take notes. And we'll start in about 5 minutes. Thanks.
So there's, on your microphone, there should be an FCC ID. Can you read that FCC ID off for us?
Uh-oh. Am I setting myself up for trouble here?
Well, no, I don't think the FCC ID will help that much because depending on what you get, they all program them to a slightly different frequency. What?
Give us a clue about what frequency we should be.
No clues. This should be pretty easy.
It's on the front panel.
What's that?
Come
On
on.
the transmitter, there should always be an FCC ID.
Oh, there is. But yeah, no,
Well, let's see if we have it.
it won't be hard to find, especially if somebody's actually outputting the signal. Look, it's all right there.
Well, that's a frequency, but
Yeah.
I'm saying there must be an FCC ID.
Is the FCC ID
It's not listed there for some reason.
Okay, we're using improved gear. Don't worry about it. All right. So now, Neil, what we're going to do now is we're going to live stream Neil's screen.
Mm-hmm.
And then you'll be able to follow online, and we're also going to try and put it up here, so you need to hook it up to the external projector now.
Oh,
Or should we just put VNC up there?
sure. Whichever's.
Let's have a look at that. All right. Did anybody from the internet audience have any questions? The last time I went to DEF CON, it was number 7. I have a hat somewhere. Whoa, we might see you at the next one. My company only sends upper echelon brown noses to DEF CON. Probably gets you right there. Who's got a wicked sense of humor? Okay, so you're running the VNC7 then?
I think I am, yes.
All right, so
Yeah.
I'm going to start then screen sharing. And
Yeah.
your IP address was 10.20.1. What?
1 second.
107?
1.108.
108.
Yeah.
Password. Should be password. Question: why is the image so blurry? I don't know. 192.168.0.08 laser. You only. Connect. Okay, I'm not able to connect to you. Of course, this is work. Are you logging anything, Neil?
No, I'm not doing
Do
anything.
you have a firewall on?
No.
Don't worry about the camera. We're going to stream the display. What is it listening on? PTG 900?
Oh, there we go. Disable this.
That's true. I did ask for questions.
Yeah, 1.8. Sorry, 1.108.
All right, here we go.
Oh, there we go.
That's your whole screen, right? Is that your whole screen?
Yep,
Ew.
pretty much, yep.
I'll just bring it up on the live stream and we're good to go. Do you want to start talking and then I'll
Yeah.
explain what's going on?
Okay, so I will talk about, this is the second installment in this ongoing GNU Radio USRP tutorial for beginners, newbies, people new to the SDR world or the USRP devices. And today we'll talk about FM receive and RDS. So first, before we start, I'd like to give a shout out, give a special thanks to a colleague of mine, Nate Temple. You may remember Nate. He was here at Cyberspectrum at Noisebridge back in September, and he presented his Etch and SDR embedded SDR device. It's an embedded Odroid device. So special thanks to Nate. Just want to recognize Nate and his help. So I'll talk about FM and analog modulation schemes and go through some slides and some theory and some talking basically, and then I'll switch over to showing some demos and we can go through. What is FM? So the idea is let's talk about analog modulation schemes. FM is one of 3 different analog modulation schemes. And what is an analog modulation scheme? Well, it doesn't encode bits, and it's a way of transmitting information from a continuous time analog source. So anything that's not bits, any continuous time waveform that you want to transmit uses an analog modulation scheme to do that. And when it transmits that information, it has to do so over a carrier, and that carrier has to be modulated. And if you think about a carrier is sinusoidal. And so with the sine wave, there's really 3 things you can change. You can change the amplitude, you can change the frequency, or you can change the phase. And so each one of those gets its own name or modulation scheme where you're changing one and holding the others constant. So in amplitude modulation, you're modulating or varying the signal strength, the amplitude, and the information is encoded in those amplitude changes. In frequency modulation, you're encoding the information in the instantaneous frequency of the carrier wave. And in phase modulation, you're encoding the information in the instantaneous phase. So those are the 3 modulation schemes, analog modulation schemes. This diagram, unfortunately, didn't come out very well, but I have some others that illustrate this. So here you have, up at the top, a carrier wave, the sine wave that I showed on the previous slide. And then you have a modulating sine wave, and usually it's not a sine wave, it's some information like, say, your voice, an audio signal.
We're going to do a live demo of that.
Are you going to set that up? Okay. So with AM, the amplitude is what changes, but the frequency and phase remain constant. With frequency modulation, which is down at the bottom, the amplitude and the phase remain constant, but the frequency changes. And in the middle, the second from the bottom, is phase modulation, where the phase of the waveform changes. But again, the others, amplitude and frequency, are held constant. There's another picture showing the same thing for AM and for FM. With FM, one issue that comes up and becomes important is how much bandwidth does an FM waveform take? And there's something called the Carson's bandwidth rule, which a guy came up with almost 100 years ago. There's a guy named John Carson. He did a lot of research on FM back in the day, and he was the first to present this equation, which is pretty simple. And the idea is that the bandwidth, the approximate bandwidth, this equation is not exact, or this rule is not exact, but the approximate bandwidth used by an FM transmission is equal to twice the peak frequency deviation from the center of the modulated signal. So in other words, by how much does the frequency vary in the carrier, plus f of m, f sub m, which is the highest frequency component in the information signal. So in the case of commercial FM that we know, the highest frequency content in the information signal, the audio, is 15 kilohertz, and the frequency deviation is 75 kilohertz. That's just an FM standard that's used in the US. And so if you go through the math, you get about 180 kilohertz. And I'll talk more about this in a minute, but when we say that an FM channel is 200 kilohertz wide, why do we say that? This is why we say that. So FM broadcasting, how does that work? And we're familiar with this, I'm sure. FM radio is between 87 to 108 megahertz. Not all countries follow that, by the way. Some countries are lower than that. I don't think any are higher. But in Japan and parts of Europe, I think it goes down to 76 megahertz. And not all of them go up to 108. But in the US, Canada, it's 87 to 108. And the channels are 200 kilohertz wide. And that's because of the Carson bandwidth rule that I just talked about. And they're aligned to multiples of 100 kilohertz. All the stations end in 0.1, 0.2, 0.3, something like that. And the channel spacing is 400 kilohertz. And here I mean the local channel spacing. So in a given market or geography, the channels won't be any closer. So if you have a station at 94.5, you won't have one at 94.7. It'll be 94.9, if it's close enough. If it's far enough, then the FCC will assign another channel on 94.7 in this example, but not in the same geography. The FM broadcast system was originally mono, and then stereo was added later in the 60s. And Carlson's bandwidth rule explains why those frequency assignments and allotments are made. FM channels are 200K in width. So what does an FM radio spectrum look like today, a modern FM radio spectrum? So here's your mono information right here, your mono audio. And this was the original FM spectrum back in the day prior to the 1960s. And this was originally mono, but then what happened when they added stereo was they said, let's let that audio component be the left plus the right channel, and we'll add a stereo component here between 23 and 53 kilohertz. And so that's your stereo component there that's left minus right. So if you take the left plus right and the left minus right and you add them and difference them, you'll get a left and a right channel. And that's how stereo is implemented. The older receivers that didn't have the ability to tune this high or to receive the stereo subcarrier would just ignore it, and they would just get the mono channel between 30 hertz and 15 kilohertz. Here there's a stereo pilot tone that indicates the presence of a stereo signal. And 3 times this frequency is the subcarrier for stereo. And that's added by the receiver. It's not actually transmitted.
Neil, could I add one point on the old days versus the new
Sure,
days?
yeah.
I mean, the nice thing was that they originally had the mono mix here because you just listened to mono and made the receiver simpler to implement. And then as they added all these subcarriers, the thing is it kept it backward compatible. That was the key thing. So you can filter out all of the other subcarriers at higher frequencies, and if you use an old receiver, it will still pick up just mono audio without all the new stereo stuff. And what's also interesting, just came to mind, is that on the analog, say, FM receivers, the big hi-fi decks, they'd have the stereo light sometimes.
Yeah, right, I remember that.
And so that would actually look for the presence of this 19 kilohertz stereo pilot tone, and if it found it with a good enough amplitude, then it would light up the light to tell you, yes, you're receiving a stereo signal, and then do the stereo.
Right, yep, exactly. I should have mentioned that. The system was designed to be backward compatible, kind of like analog video, TV, NTSC was originally black and white. They added color later. So black and white sets can still receive color transmissions, but color TVs can receive the color information. So these systems were made backwards compatible. And then some other interesting things higher up. There's this RBDS or RDS that we're interested in today. And this is up at 57 kilohertz. And it's a 4 kilohertz wide signal I'll talk about in a minute in more detail. And that's where the digital information is encoded. And that's where the modern receivers, like say in a car or I don't know, some FM receiver on your smartphone or something gets all the station ID and things like that. There's a few other things here that are kind of interesting. I don't know much about these, but there's this other audio subcarrier here, which is like a shadow station. And it's often used for things like elevator music or alternative broadcasts that a station might get revenue for, like music that might play in a store or a mall or some kind of background music.
Do you remember when we were in Washington, D.C.,
Yep.
just on the back of the last special Cyberspectrum from over there, and we sat down with Tim,
Right.
Tim K,
Tim O'Shea,
who you might remember did the shock collar
Oh,
demo on his leg, and we actually looked at this, and we saw another subcarrier out there, and it looked to be containing some sort of information. We weren't sure if it was analog or digital, and then we actually, played around the flow graph a little bit, put a, I think it was just narrowband FM demod out here, and we actually got elevator music or something to that effect.
Right.
So if you're in your area, wherever you may be, just have a look at the spectrum, and Neil will show you how to do that in a minute. You can investigate and actually see whether there are other subcarriers there, and just try and demod them, see what it is.
I forget if it was with you, Balint, but there was one story about how, I guess, a local Bay Area hard rock station had Bollywood music on its subcarrier. So it's not even like the two audio streams are related necessarily. They could be completely different for whatever business or marketing reason. Here's another depiction of it, a little bit more maybe easier to see or artistic with color, just to show some other things here. That, for example, this RDS subcarrier is 4 kilohertz wide, and it's much lower in amplitude than some of the other pilot tones in the signal. So this is another depiction of the same thing. And then the RDS, which is also called RBDS in the US. Let's take a look at that more closely. So RDS is actually older than you might think. It goes back to 1984. And it is a standard for embedding small amounts of digital information into commercial FM broadcasts. And there's a lot of stuff in there, such as time, station identification, program information, radio, what they call radio text, which is basically the currently playing song, title, and artist, and a bunch of other things I'll mention in just a minute. And the RDS signal is 4 kilohertz wide. It's a BPSK signal, binary phase shift keying signal, and it transmits at a data rate of 1187.5 bits per second. It's not very fast, but it doesn't have to be. It's just transmitting some basic information.
And it also conveys TMC, which is the traffic message channel that sends info to your nav system in your car, for example.
Yep. I mentioned that a little bit here. I don't have anything to look at it in, particularly or closely, but I have a list of some of the information that's transmitted on RDS. I think I mentioned this, that the subcarrier is the third harmonic of the 19 kilohertz pilot tone, and there's error correction on this as well. And then these are the fields, the information fields for RDS. Here's the traffic information down here. Each information field has its own name or acronym, AF, CT, and so on. There's time. There's alternate frequencies which tell the radio other frequencies that they can tune to get the same station if the primary signal, the signal that you're tuned to, is too weak. There's program identification, the program service, the radio text, which is the information about, typically the information about the song, traffic information, and then TMC, which I thought was for like emergencies or like traffic avoidance or some kind of broadcast notice. So that's RDS, and we'll take a look at how to first demodulate FM and then how to demodulate and obtain the RDS subcarrier. The tool that I have to do that here with me attached to this laptop is this device here, the B200. The one I have is actually the B210. The only difference between the two is whether it's one channel or two channel. So the number of SMA connectors on this side of the board here. There's either 2 or there's 4. And I'll go through the installation of all the software tools. I don't know if you want to do this, or if you've already done this or you're familiar with it, we can skip it, or if it's useful to people, we can look at it more closely. It's all really up to you. This is kind of a tutorial. It's not really a talk per se. So it's guided really by the audience. So the driver to use one of these USRPs is called UHD, and it's cross-platform. It runs on Mac, Windows, and Linux. It's open source, and it's hosted on GitHub. So you can download it and install it, and I'll show you how to do that in just a second. And basically where UHD sits is kind of here in the middle, where you've got the USRP radio, the hardware. On top of that, your operating system, and then UHD is a user space driver. It's not a kernel space driver. And it sits there between whatever framework you're using, like MATLAB or LabVIEW. You can use C++ directly to program interface to the driver, or, of course, certainly GNU Radio. Usually, sort of the most natural, the most popular platform for using UHD is Linux. These versions of Linux are known to work well. Any version should work as long as you have the right dependencies and the right versions. But in case you're curious or you're starting this yourself, remotely or here in Noisebridge, these are the ones that we would recommend. Ubuntu works really well, works right out of the box, very easy to set up. Any of the long-term support LTS releases work just fine. 14.04 was the previous one, and another one just came out a month or two ago, 16.04. The other interim releases should work fine as well. Officially, I think these drop off support after 9 months. And Ubuntu, you may know, you may be familiar, has these like respins that are still Ubuntu, and they work the same way, but they have a different desktop environment. So there's Xubuntu or Xubuntu, however you want to pronounce it, which uses XFCE and the KDE variety. Those should work fine. Any of the recent Fedora releases should work fine. And Red Hat Enterprise Linux or CentOS 7 should work fine as well. So if you have that on your laptop, you should be good to go. Again, Windows and Mac work as well. Windows 7, Windows 8, Windows 10, and any of the recent Mac OS releases. So to install UHD, you follow these steps. This is building from source. There are other ways. I'll explain in a minute how you can install UHD from a binary package. But building from source has some nice advantages. You can easily change versions or jump onto different branches. You can modify the code and rebuild it if you want to do any kind of development or modify the driver or add any debugging information or something like that. So it's just more flexible, and it's kind of fun to learn how to do that and get that working. So it's not hard, assuming you have a stock installation of any of those other Linux versions I just showed on the previous slide. You follow these steps. This sudo apt-get install step is Ubuntu specific. If you're on Fedora or Red Hat, the command will be a little bit different, probably sudo yum install, Y-U-M install, and the package names might be different, or some of them might be different, but go ahead, questions?
How painful is the Windows build?
The Windows build is pretty painful. You can use Visual Studio 2012, 2013, or what is it, 2015, I believe is the number. Whatever the 3 most recent Visual Studio releases are.
There's no main build?
Sorry?
There's no main build?
Uh,
I forgot.
Oh, okay, I know what you mean. No, I don't think there is, or I mean, I think that's going to be even harder to get built.
Okay.
Yeah, just Visual Studio, and there's a bunch of dependencies like Boost that you'll have to install first, and then yeah, you can build it in Visual Studio. It does work, but I haven't done it myself. I'm more Linux centric, but yeah, Mac is pretty easy though. And then after you install those dependencies, these are the only ones you should need beyond the default installation. So assuming you have a fresh install of Ubuntu, these packages and only these packages are required. You can just install this and you should be all set. And then you clone the repository that UHD is hosted on from GitHub. You clone the repository from GitHub. With that command, it shouldn't take too long. You go into the folder that gets created, UHD. You switch releases, to the tagged release for the most recent version, which is 3.94. Then you go into the host folder. You'll see a folder there for host. There's some other folders for FPGA and firmware and a couple other things. You want the host folder. And the way both UHD and GNU Radio work is they're built with CMake, and so there's this sort of same series of steps you'll see over and over again for building out of tree modules or building GNU Radio or building UHD. You make a build folder. It doesn't have to be called build. You may want to tie it to the version that you're building, but for other reasons I'll explain maybe later, but most commonly it's called build. So you make a build folder and you go into it, and then you invoke CMake. The ... just means parent directory, so it'll get all the CMake configuration files from the folder above. When that runs, it'll tell you what components are enabled. Assuming most of the components are enabled, or the ones you're interested in, or maybe all but just a few are enabled, you should be in good shape. If you see E100 and E300, there's a usurp device called E100, E300. If those aren't enabled, you should be fine, of course, unless you're using an E300, but we're probably not here, so you should be fine. And then when that completes, it'll create make files, so then you can invoke make. The J4 just means use 4 cores and do a parallel build, so it'll speed it up quite a bit. And then when that finishes, probably takes, depending on the speed of your system, anywhere between maybe 6 or 8 minutes to 20 minutes. And then when that's done, you can make run make test. That's optional. It'll run some tests. And then you do a sudo make install. And that'll install it under user local. And you need the sudo because you need root permissions to write to that folder.
Can I just add a couple of comments here
Sure.
from IRC? Somebody's asking, did someone find the wireless mic frequency, or was that my speakers messing up? Any luck with finding these signals yet? Someone's found
Oh,
it down
please
the
have
back?
mercy on me.
Yep.
197.111 something.
That's correct. Do you have a look already?
You're a winner.
Looks like somebody's got it.
And I didn't need the FCC ID.
What? Yeah. I think you're off ever so slightly because frequency offset and all that.
Cheap SDR.
He's got a cheap SDR. That'd explain it. What SDR do you have?
The RTL.
The RTL dongle. Yeah, that'll give you a little bit of frequency offset. And unfortunately, too, it's receive only, so we don't have to worry about.
Yeah, but now the
such a
frequency's
over-
gotten out there.
Overriding things.
Well, one of
But
them.
for everyone else, got a bit of a hint. There's another frequency to discover, though. That's just one of two. Let's see. Not sure if capital A, capital F is used in the US, but in Europe, many stations take advantage of it. You can drive for a long time listening to an FM station, and the radio will retune automatically to local transmitters. That's what you were talking before with the RDS, giving
Right.
the
Right.
frequencies. Some NPR stations use it. It's not very common. The retuning is almost unnoticeable. I've never actually seen it myself, but it sounds like a pretty cool system. Let's see. UHD and GNU Radio work very nicely in Debian Jessie, which is Debian 8. I install from Jessie dash backports typically. Somebody was very complimentary and mentioned if you just want to use an SDR with WinRAR or HDSDR or something like that on Windows, you can use the XDIO plugin, XDIO usurp. There's also SDR Sharp. Somebody's HackRF just came in the mail today. And actually there's a suggestion, if you wanted to use it under Windows, if Windows is all that you have on your laptop, you can use the GNU Radio Live DVD, which you can also use to burn onto a live USB.
In fact, I'll go into that.
Okay.
I'll do a
Neil's going to talk
breakout.
about that in a minute.
I'll do an aside
Actually,
about that.
Nate mentioned that.
Oh, did he? Okay.
So thank you, Nate.
Thank you, Nate.
Somebody else had the HackRF arrive yesterday. Let's try something fun. So there's actually an RTL dongle running at Noisebridge. The IP address is 198.207.77.2 on port 1234. That's running the RTL TCP server. So have a go at that. All right, back to you, Neil.
Okay.
I put together that whole flow graph, by the way, so
Oh, you did?
we can demo that
Okay.
whenever you want.
Yeah, sure. Absolutely. Thanks. So that's, nice, easy 11 steps to getting UHD installed from source code. It's actually really not that bad. And if you're not familiar with building from source or maybe using the command line or doing, git clone and things like that, don't worry too much because these steps verbatim should really work out of the box, especially on Ubuntu. You shouldn't have a problem. If you want to install from a binary package, you can do that too. Starting with UHD version 3.9.2, Edis Research has started putting binary packages providing binary packages for Ubuntu through Launchpad. So you don't even have to download the Debian file from any website or anything like that. You just run these 3 commands. You have to add the repository to your database of repositories, local database, do an apt-get update, and then install UHD host. I'm not even sure if you need all 3 of these, but if you install all 3 of these package names, you'll get UHD. And that's the easiest it really can be on the Linux side. Just using these 3 commands, you can install pretty quickly, probably within 5 minutes, without having to build or compile anything. And that'll work for, like I said, any version after 3.9.2, so 3.9.2, 3.9.3, 3.9.4. The only catch is this is only for Ubuntu. There are RPM packages on the Edis Research website for building for Fedora, but installing for Fedora and Red Hat Linux. So you can use the RPM package as well. I'll talk about another way to build UHD or install UHD a little bit later. It's more in line with GNU Radio, so I'll talk about that in a second. Once you have UHD installed, there are 2 utilities you'll probably want to know about to query the USRP. The first is UHD find devices, and that will go out and look to see what devices you have installed on the network or USB or whichever place, and report back what it is, what address it's on, or what the serial number is, and what type of usurp. So you can take your USRP, plug it in, say the B series device, plug it in. If it's a N or X series that connects over Ethernet, you can run this and check that the device is there. The probe, there's another utility called probe. It basically just tells you more information like serial number and so on. I'll leave this. You can read these slides and go through it, try it on your own later on. I included this just for reference. You may have to download the images, but we'll see that when I run through the demo and we run through the stuff. I listed a bunch of other reference material here. You can play with this later offline. There's all kinds of utilities you can run once you install UHD. I'll go back to it if we have time, and it's in the slides for reference. GNU Radio, just a quick mention here. Probably most of you know what GNU Radio is and certainly have heard about it. The GNU Radio conference is coming up, by the way. It's a really great event. It's coming up in the middle of September. This will be the 6th year running it, so if you have any opportunity to get out to Colorado, it would be really a good event. It's a week-long event all about GNU Radio. It's like 250 people. They might even hit 300 people this year.
And I hear we're going to have an absolutely incredible wireless hacking challenge this year.
Yeah. Want to say anything about that? Yeah, there's a lot of good events at GNU Radio Conference. If you can make it out there, I think it's really worth it. So
it's been growing by leaps and bounds every year. And then, yeah.
Yeah, so check it out. There's a web, if you just Google GNU Radio Conference 2016, we'll go to the homepage. You can get more information about it. It's coming in about, 3 months, 2 months? So installing GNU Radio, again, you can install from source. There's a few more dependencies here. So this might take a little bit longer than UHD to install, but just copy paste this exact list of dependencies should work for Ubuntu. The package names are almost definitely different for Red Hat. Not too much different in some cases, but they're going to be different. So it's not a slam dunk to change the sudo apt-get install to sudo yum install.
I hear all the cool kids are using PyBombs these days.
Well, I'm getting to that. And then the rest of this sort of recipe should look familiar. You do the clone. You might notice this recursive option. Why is that there? Kind of a long story. The quick answer basically is there's a component that's called a submodule that's required for GNU Radio. They broke it out separately because you might want to use it by itself, but with GNU Radio, you definitely want to include it, so you have to do the recursive so it knows to get the submodule. If you don't do that, it won't work. So include the recursive.
What submodule is that?
It's called VOLK, V-O-L-K. It stands for the Vector Optimized Library of Kernels. There's basically assembly-level primitives that optimize DSP operations for your specific processor. It speeds up things quite a bit, so it's a required component to run GNU Radio. But it's also useful outside of GNU Radio, so they broke it out as a submodule. You'll see a GNU Radio folder once you do that, so go into that. Check out the specific tagged release. The latest version is 3.792. And then the rest of the recipe is the same as for UHD. You make a build folder, you go into that, you invoke cmake, you kick off make, you do a make install, and you do the ld config, and then you're done. And you don't have to reboot or log out or anything like that. You can just go through these steps as they're shown here, and it should work. There are other ways to install GNU Radio. There's something called PyBombs, which stands for Python Build Overlay, et cetera, kind of a funny acronym, or I never remember what it stands for without looking, but PyBombs is basically a package management tool for GNU Radio, and it also manages, it's a package management tool for GNU Radio and out-of-tree modules, but it also can actually install GNU Radio itself, as well as UHD. And it's made up, basically the way it works is you define recipes to explain to the tool how to install something. So it really can install anything. And it's used with a lot of out-of-tree modules to automate the installation and management of those out-of-tree modules. It's kind of similar to RPM in the Red Hat world, or pip in the Python world. A new version, 2.0, came out with a lot of changes and updates. So it may be a good time to start playing with PyBombs, and here's the URL if you want to get more information about it. There's also a build GNU Radio script. I'll give a shout out to another colleague of mine, Marcus Leach. He's at the Shirley Bay, or was at the Shirley Bay Radio Astronomy Consortium. And he put together a really, really useful script that will build from source UHD, GNU Radio. It'll install all the dependencies. It basically will automate everything that was on the previous slides, all the manual steps in the previous slides, and do everything for you. It takes, it can take a long time to run depending on your internet connection, the speed of your internet connection, the speed of your system, but it's a way of just automating everything that you might do manually. So it's a really useful script, and you can pass options to it to specify certain branches or certain tagged releases that you want to use, or if you want to put it in a certain folder and things like that. It is customizable. So that is another option. And then there are PPA packages, Launchpad packages for Ubuntu, but the problem is they're old. They're usually old. So one caution I would say is don't install GNU Radio from apt-get. Either install it from source, install it through PyBombs, or install it through the build GNU Radio script. And also for Windows, GNU Radio is notorious, or has a reputation or history of being really difficult to install on Windows, and it is. It does work under Windows, but it's. I mean, I've never done it. I've heard horror stories about it, and I've just heard a lot from people that it's very difficult. There is one company in the DC area. I forget the name of it, but if anybody's interested, either email me or just Google it. You might find it. It's also on the mailing list. It's been mentioned on the mailing list. Forget the gentleman's last name, but the first name I think is Jeffrey or Jeff. And he's from a company that has provided graciously Windows installers for GNU Radio. And so this process becomes immensely easier with those tools. So those are provided freely, and you can take those and install on Windows. And I've heard they work pretty well under Windows 8, Windows 10. So you can get GNU Radio running under Windows.
Check this out. Building on Windows with native tools. PowerShell scripts are now available that fully automate the build process for 3.792 plus.
Oh, I wasn't aware of that. Okay.
And you can even use Chocolatey. If you've not heard or used Chocolatey, it's a really cool package manager for Windows. It looks like, it's supposed to actually go to the web page. If you go to Chocolatey, can't be reached. Did
I think you misspelled it.
Choco. You mean? Yes? Waiting?
Yeah, go ahead, click it.
Hey?
Click.
I did it.
Oh, it's waiting. Okay.
Maybe they're experiencing too many users. Anyway, there are options out there. So if Windows is really a thing, then you can persevere with that.
I got Wireshark to build, so I think I can probably make my way through GNU.
This gentleman just announced impressively that he got Wireshark to build on Windows. So if you can manage that, then surely.
It was not fun.
Yeah, that's an
actually,
accomplishment.
we've got a couple more comments in IRC. So old PyBombs is old. Use the PyBombs 2 now. And another suggestion is, one thing I learned, pick one method and only use that method. If you start using a whole bunch of methods on your system, you'll probably end up conflicting with things. So for example, on Mac, you can use Homebrew or MacPorts. I'm a MacPorts kind of guy, but Brew will do it well as well. And someone else points out that on new Fedoras, don't forget that it's DNF instead of Yum.
Yeah. Yeah, starting with what, 23 DNF, yeah.
So Patch Von Broad says, you can even ask build-GNU Radio to fetch and install OOT out-of-tree modules when it's all done with the other stuff.
Cool.
And actually, I think we've got a very, very special friend tuning in all the way from Australia. Some other people announced that they were tuning in from places where it was 2 a.m. and 5 a.m. My friend Matt Robert is tuned in from Australia. He says hi.
Hi, Matt. Thanks for tuning in. Okay, maybe I'll digress for a minute, talk about the live USB really quick, just to show that. Oh crap, how do I get out of full screen mode? There we go.
I have a question regarding the
You want to
Sure.
use the microphone?
the question I'd have about the installing GNU Radio and USRPs. Options to compile on a PC and then port to an ARM processor such as Pi. Any advice on doing so?
Yeah, so generally when you're going to run it on some embedded device like a Raspberry Pi or what have you, you've got a couple of options. One is to compile on the device, which is usually incredibly slow and painful, and GNU Radio will probably take a week. Not only that, remember that when you use Swig, it's got to generate wrappers for all the Python wrappers for all the C++ code, and so when it does that, it can generate absolutely enormous compilation units that can take gigabytes of memory. GNU Radio has been pretty good about splicing that up, but that can still be a problem. The alternative then is to cross-compile, which means that you need to get the tool chain for your target on your computer that you're going to use to build your release. Oh, GNU Radio's got this fantastic new website, which you should check out. We've got blogs and all sorts of cool stuff, fancy graphics. But essentially, what you want to do is you basically want to find out what embedded device you're targeting. You need to find the tool chain for that, and then that'll usually be available for, say your normal PC. You can set up the tool chain on that, and then what it'll do is it'll tell the environment to use the special compilers that will cross-compile to your target, to the ARM platform, for example, the ARM architecture, and then it'll just do all that, and then you can, when you deploy it, you send all your targets and your build outputs to there. Just thinking from personal experience with the USRP E310, for example, you could download a single big blob. It'll extract the entire ARM-based tool chain onto your computer with all the libraries and everything you need to use. You run a source script so that it sets up all the environment variables, and then when you type in GCC or whatever, it runs the ARM cross compiler and not your native compiler. And then you can just do all the same stuff, CMake and make, and when you make install, instead of when you do make install, you don't make install onto your local computer. The trick is that you can mount, let's say you have your Raspberry Pi running or whatever, you hook it up by the network, and then you mount its file system on your build machine's file system. You can use something like SSHFS, which is a file system passed through SSH, uses Fuse, and then you can do make, install, and then dest dir, D-E-S-T, dir equals, and then give it the prefix to your mount point for the remote file system. And that way, make install will just send it all through automatically. And then you'll have it installed on your remote machine. Compiling on the Odroid C1 took me about 8 hours, and I had to use an external hard drive and mount a swap file for it to compile.
Yep. Who said that? MyBit?
Yeah.
Yeah.
So the recommendation is try not to compile it on your embedded device. Try to cross-compile, and then you should be good. Back to you.
Sure, yep. Okay, so I'll digress for a moment. Just want to mention this live SDR environment. GNU Radio has this ISO image that you can download if you don't want to bother installing anything, or you can't install anything. Maybe you're not allowed to install something on your computer, or it's a policy at your office or something like that. Or
Does anybody have a laptop and actually want to try booting it up now?
Oh yeah, you have
I've got a couple here. Is there a hand down the back?
So this is a way to just quickly get started. You don't have to worry about installing anything, or you want to maybe just test something out or whatever. You can download this ISO image, write it to a flash drive, and then boot off of it, and you have a Linux environment that comes up, and it has all the tools pre-installed. So you have UHD, GNU Radio, and also GQRX and a whole bunch of other tools. So everything is installed, latest or almost latest release, so it's current, and you're good to go. So this is provided from the GNU Radio website, and there's actually 2 pages. This is the page where you can download it, and it comes with the latest version of GNU Radio 3.792, and then it has a whole bunch of software here that's listed here, like Osmo SDR, OpenLTE, Air Modes, GRAIS, and so on and so forth. There's a whole bunch of stuff here. GR Paint is really cool. They're all really great, useful utilities. GRGSM, I think, is here as well. And of course, GQRX, which we'll talk about in just a few minutes. And I think a pretty recent, or the most recent release of UHD is also included, along with drivers for other hardware devices as well, like Blade RF and RTL SDR and so on. So everything's in one package, and I guess it's 391 is the UHD release. So not the most recent, but a pretty recent release. So you download this, it's an ISO that's about, I think, 1 1/3 gigabytes. Write it to a USB drive with this UNet bootin tool. You may be already familiar with this. It's a free tool that runs on Windows, Linux, Mac that will write a bootable image to a flash drive. Or on Linux, you can use DD, the utility DD, to write it. And then boot off of it, and then you'll get the live environment, which the new GNU Radio website, which is a really nice, they did a really nice refresh on the GNU Radio website. And they have a page now for the live SDR environment, which will walk you through what you can do after you boot into it. And so you boot it up, and it shows you some quick things you can do to get started and play around with it. So you can read these 2 pages. And the person who put the live USB image together is Jonathan Corgan. He's a key member of the GNU Radio project. And so that's the GNU Radio. So that's yet another option to install this stuff, is the live USB. Okay? And then now let's dive into the FM stuff. I'm going to, again, just kind of run through these slides very quickly because it's more for reference. There's a bunch of utilities that are, even though it doesn't say GNU Radio, they're GNU Radio under the hood. So there's a spectrum display tool. There's a signal generator tool that's console-based, one that's GUI-based, graphical-based. You can use the slides as reference to play with this and run these tools. And then GNU Radio Companion. And I think some of this I covered last time. I'll cover it on the fly as we go. And I'm going to skip these introductory basic flow graphs. I think we talked about them in the last tutorial. If we have time or there's interest after, at the end of the evening, we can go back and look at it if you want to. But I'm going to jump ahead to the FM radio. And so what we'll do here is create this flow graph, which uses a USRP source block, which represents the radio. Samples will be generated in this block. We'll send them to a frequency sink, which is basically a spectrum display. And then we'll go through a low-pass filter. We'll do a rate change, send it to a wideband FM receiver, which will do the FM demodulation, resample it so that it's at an audio sound card compatible rate. We'll have a constant multiply here to adjust volume. All this will do is adjust volume. And then we'll put that to an audio sync, which is basically your speaker, your sound card. We'll also write it to a WAV file. So we'll basically record what we tune to. And let's have a look at that. So I'm going to bring up that flow graph. I've got a bunch of stuff here.
Shall we skip my thing? My flow graph?
Oh, no, it would be nice to show, though. We'll see how we do for time.
FM. You want to do before this or after?
But since I have it up, we'll do it after. OK, so here's the flow graph that I just showed. Again, I'll skip some of the details here. We can go into it after the evening if you have questions about, say, what these colors mean, just data type for the ports and how GNU Radio works, and you have variable blocks and things like that. Each of these blocks you can select, and they have properties. I'll just go ahead and run this flow graph, and what happens is you design or put together these blocks and interconnect them, and then you hit this run or execute flow graph button, and it generates a Python flow graph under the hood. And so a .py file gets generated and run. And so I'll do that. And in this window here, you see the console output. And so there's some UHD debugging or status information. And then I'll tune to a station. I know that, sorry, that's the volume. I know that 88.5 NPR is pretty strong. So we're here at Noisebridge. We're here at Noisebridge, and Sutro Tower, one of the biggest radio transmission towers in the Bay Area, is literally out that window facing us. And so we're being blasted by FM radio. So I have this antenna here, what is this, maybe half a meter or something antenna. I don't even really need that probably. Putting the microphone close to the speaker. Can people hear it?
John, that the seats that you were sitting on, probably a lot of the things you're wearing, the toothbrush that you woke up this
So
morning,
this is not
I guarantee
demodulating any of the RDS.
products and
This is
everything
just
else
a
is on
mono,
the
it's not stereo
trade,
either.
products, including
This is just a
sound
mono
and
FM receiver
also
that is also recording to
by the way,
disk.
your house prices might be going up, or you might be having challenges affording a first place because people.
You
from
look at the file
Zhejiang,
system,
as
you
well
can
as elsewhere in
see
China. Within China, people don't like the people from Wenzhou because they're seen as the.
there's a
Beverly
WAV file
Hills,
being
you know.
recorded here.
And so I think the story of Jack is also a story of.
So I'm basically recording what we've tuned to, and this graphical environment, where did it go? This window here is constructed with these QT blocks, the QT frequency sync, and this audio gain slider, and the slider for the frequency and the slider for the RF gain. Those three blocks control these three sliders here. And so this is for tuning, this is for gain on the RF stage, which we don't need because we're being blasted from Sutro Tower already. I probably don't even need the antenna. And then this is basically volume. And this is the FFT, the spectral display. So that's FM. Any other station anybody wants to try just quickly while we're here? I don't know all the stations.
I'm the last person really to see
Okay.
it before we launch it.
So that's simple FM. And then we'll use the GR-RDS out of tree module to look at it a little bit more closely and get the RDS subcarrier. And I'll explain a little bit about what these out of tree modules are. So these, what are called OOT modules, out of tree modules, are components that don't live within the GNU Radio source tree, and they're not part of the core distribution. They are modules or third-party add-ons to GNU Radio that provide additional functionality and blocks that you can use in GRC. And there's a directory of these out-of-tree modules at CGRAN. You can go to the website, take a look. Keep in mind, it's not a hosting site. It's just a directory. It's just a listing of out-of-tree modules. Most of them are hosted on GitHub, but the directory, the CGRAN site will point you to the GitHub pages for the modules. I'm going to skip this for now. Again, it's more for reference, really. This is what the page looks like, the CGRAN page. Okay, you got it up there live, yep. That's this. And you can see there's a long list of modules. Some of them are more active or actively maintained than others, but there's all kinds of stuff there for digital video, ATSC, LTE, GSM, just all kinds of different things, 802.11, pagers, restaurant pagers and things like that, all kinds of stuff. So how do you build an out-of-tree module? It's the same recipe. You clone the repository from the out-of-tree module. You go into the folder, you make a build folder, you go into that, you run cmake, you run make, you install it, and you run ldconfig. It's the same recipe. So we'll look at GR-RDS, and I've already installed it, and I can show you what that looks like really quick. Okay, yep, I'll change them. Yep, yeah. Might be different in XFCE. Sorry. Where's the, do I have to? Is that better? Everybody see that? Crap. Okay. Okay, so there we go. So there's GR-RDS, and those are the folders, and I've got a build folder. I've already built it, so I won't go through that process, but you would literally type the same commands I showed on the slide. So you can go through and build that, and then you've got RDS, and when you do that, there's a folder here called apps. And if you look at the apps folder, there's an RDS receive, an RDS transmit, and a loopback. So there are flow graphs here that the authors provided that invoke, use, and demonstrate the RDS out-of-tree module. So let's have a look at that.
I might just add that if you just Google GRDS, the first hit is the GitHub page, and so you can see everything there. And Neil would have checked this out. So if you just copy this
I have it here.
URL, then you would check it out.
Right here. Oh, sorry, that's UHD. So there's UHD. I'll just quickly go through these. There's the GNU Radio GitHub page, and then here's GRRDS.
And then also, PyBombs, for example, has a recipe for RDS, so that would give you a really quick way to install that too.
Yep. Okay, and let's run this. And this flow graph is more complicated. There's a lot of different things going on here. You have a stereo receiver and you have the RDS, and here's how that works. Here you've got the USRP source, and that feeds into a frequency translation filter that moves the signal down to 250K. And then there's a bunch of trees here, legs. You have a leg here for the RDS that does the BPSK, the binary phase shift keying demodulation, and feeds that all the way down here to these blocks that actually do the RDS parsing, decode all the bits that are coming across, and displays that in a panel, in a GUI that we'll see in just a minute. There's the left plus right, one of the two stereo channels, the left plus right channel here, and the left minus right, and then the pilot tone, the processing for the pilot tone. And all of that goes here to different GUI objects. Here we've got a FFT sync to show the spectrum display, scope sync for time domain plot. And we'll see each one of these GUI displays as a page in the GUI that I'll show you in just a minute. You have the de-emphasis, and FM, there's some emphasis that's added for higher frequencies. I won't explain that in detail, but you have all of these steps for the two stereo components, the left plus right and the left minus right. Those two come down this path here, and there's added and subtract to get the left and the right. They're de-emphasized. There's a multiplication for scaling. They're resampled for the audio rate, and then they're sent into this audio sync block to your speakers. And that's in a 5 seconds. That's the overview of how this flow graph works and picks apart the different components of the FM spectrum. The left minus right are the two components of the stereo, and then the RDS. And then if you run this, you get this nice display from all of those GUI blocks. And let's go back to 88.5.
And so he took to inventing quotes, which is something I enjoyed telling at Microsoft the other day in Redmond, Washington, was he started to
And this is NPR in the Bay Area, and it's a really strong station, basically right out the window. And all of this stuff that you see here in the console is the RDS information coming across. So each one of these tabs is a GUI object in the flow graph, a GUI block in the flow graph. And so you've got your RF gain, which we don't need because, again, we're close to the tower. You've got volume, the frequency to tune to. You have the baseband FFT display, the demodulated baseband, the left plus right component, the left minus right component, the pilot tone and the time domain, the DSB-SC subcarrier, the RDS subcarrier, the Constellation for the BPSK signal for the RDS subcarrier, and then a waterfall display showing frequency and time for your FM receive. And then the RDS information is down at the bottom. So you've got your frequency, the station name, and so on. And these are all the components of the RDS message that are being received. And this is the same kind of display you'd see, like, say, on your car stereo.
And what's nice, bringing back to what you were saying before, is that the AF, the alternate frequencies, are actually being listed here. So you can see that this radio station is actually giving you other frequencies that you can tune to, so you can have seamless coverage as you travel.
The 20-year history of Yahoo, and of course the anniversary of the.
Do you want to go back to the second tab with the demodulated baseband, and you can compare that to the graph that you had before about the allocation of all the subcarriers?
Oh, sure. Yeah.
And I actually had lunch with Jerry Yang yesterday, and it was funny. He's now joined the board of Alibaba, as you know, and he said when he was thinking about joining, am I doing this for the past because of this momentous connection? He said, no, it's really all about the future, because, you know, Alibaba has this disruptive appeal and impact. Anyway.
Okay, so recall that this is the spectrum of FM,
99, and finally,
and
after having understood the power of the internet, how to also work with government.
It's a little hard to
there,
see.
And the power of these Zhejiang exporters, he launched Alibaba in 99. And we have people in the room who actually work for Alibaba who have been swept up today. They're one of the 40,000 people who work for the company.
You're listening to author Duncan Clark.
It's a little hard to see, but here's your 19 kilohertz stereo pilot here. Here's your left plus right, and then between 23 and 53 are your left minus right, upper and lower sidebands. And then the RDS is way down here, hidden at 57. It's hard to see right in here.
But also attention because of privacy, because of internet open
You
information.
can see the two peaks coming out there, which are the
finances. Tell us about the sort of
the
north-south
RDS.
relationship you've characterized between Beijing and what's happening with Alibaba and other
Here's the
entrepreneurs.
RDS close up. It's 4 kilohertz wide, so here's the RDS subcarrier kind of zoomed in
Firstly, the rise
at
of the East
57
to some extent.
kilohertz.
You know, Jack having got
What's interesting, I think, I might be wrong about this, but I have a feeling, because we're listening to KQED, and there are people talking at the moment, they're mic'd up with mono microphones, so the audio that gets transmitted will be pretty much mono in content to begin with, and so you will be exciting the mono part of your baseband spectrum,
to be honest, would normally have been
and then you won't really have any energy going into your stereo difference channel, so we won't really see much there.
Let me try a different station. What's another good one? I don't know. One of the stations out here.
Go to something to music, that was good. There we go. So if you look, so you saw before, this was the KQED. There's a lot of energy here in the mono part and not much here in the stereo difference channel. Now that we're on this music with a lot more frequency content and stereo content, you can see that there's much more energy in the stereo audio left minus right channel. And this DSBSC, it actually stands for double sideband suppressed carrier. So what you'll notice here is that this is actually a symmetric signal, like you would see, for example, with AM, but there's no carrier in the middle, so the carrier's actually been suppressed. That's how they broadcast it. And what's also interesting to notice, if you look at the percentage signs here, it gives you, I mean, they define in the standard very specifically how much energy you give to each of these particular subcarriers, because remember, when you go and generate your final signal, you actually end up adding them all up. You add them all together, and then you modulate it in the final frequency modulation step to then broadcast out into the world. So here, again, faintly, you can see this sort of VPSK signal there as well. And we're listening to TLC.
Yeah, RDS, no, not frequent, it's a BPSK, phase shift keying.
Okay.
Yeah, binary phase shift keying, yeah.
So we've just lost the lock.
Yeah, we should tune to a stronger station. Yeah.
It's been a long time since I've done my RF classes. Can you tell us exactly how to read this constellation? Yes. Neil?
You go ahead.
So,
Interestingly, we've been talking about frequency modulation, where you change the frequency of the signal. With phase modulation, you change the instantaneous phase. And so this is an example, well, not right now. Oh, maybe there a little bit. There we go. Locked again. This is an example of phase shift keying. So you change instantaneously the phase of your original carrier between one of two states. And so the way you would read this is this is what we want to see are these two sort of groupings of sample points. And this is after you do your carrier recovery. And so when you have a grouping of points here, this is essentially one phase, and then your grouping of points here will be another phase. And because it's binary, you can only have two states. And to turn this then into a digital bit stream that you then use in your decoder, you would essentially slice around the middle. This is the simplest way of doing it. So you can consider this right side to be a 1 and this left side to be a 0, for instance. So that's one way of interpreting it. But generally, this sort of constellation plot is used to verify that your signal is there and to essentially get a sense of the amount of noise or any sort of tuning that you may need to do to your radio or to your algorithm and all the magic numbers in there that control this process. Because the block before this essentially needs to recover the original carrier, and then it can compare whether it's in the original phase state or in the out of phase, 180 degrees out of phase state, to determine your final output. And there are more advanced demodulation techniques that you can use too, but this is sort of the super support. Now, when you see it sort of beginning to blend and blur, the demodulator there is sort of losing a lot because the signal might be too weak or the gains might not be set right, and then that's obviously bad. What's interesting is when you get that, when you don't have a strong signal and you don't have a very distinct grouping, you can use things like forward error correction, and that imparts redundancy into your original signal so that if you do in fact get quite close to the boundary and some bits cross over to the wrong side where they shouldn't be, then your decoder can make use of those redundant bits and actually correct for any errors that creep in. And in fact, RDS has some error correction in it. Do you want to flip over the console?
Sure.
So here in the console, do you want to explain what's going on here?
Well, these are just all of the RDS message components being echoed on the console display. You see that in the GUI, previous GUI here. Where did it go? This information down here is being echoed in these displays. I think there's a little bit of additional diagnostic information, and I think it's printing the actual bits that it's receiving for some of the messages. And it's in, yeah.
Somebody asked about TMC before. So here you can see some examples of traffic message channel messages. These aren't actually displayed in the UI, but you can see them come out on the console. So here's an example of one. It's saying that there's a diversion recommended. It's part of a single group of messages. Certain events have a duration associated with them. So for example, if there's an accident, then they might say this will disappear within 3 hours or what have you. I don't remember what the exact possible options are. And then you have an event code associated with it. Then you look up in a lookup table. This one here is traffic congestion, speed of 40 kilometers an hour. They basically have an entry for all the different tens of kilometers an hour. And there are some other ones up there as well. Delays expected, and more traffic congestion it's at the same location. This extent and segment is actually related to the location. So remember in your car, for example, you have the map, and I did a bit of research a while back as to how the system works. Some cars, how they're hooked up with Sirius, they can actually get this message over Sirius XM as well. They have the satellite and also the ground repeater stations, or they can get it from this FM subcarrier. The information is the same. And then location will feed your nav system and actually then draw the correct segments on the right roads or the correct points where an event has taken place. So interestingly, they don't actually transmit things like latitude and longitude. It is specific to the traffic database that's loaded into your nav system. So every territory will have its own database set up. And so these codes, these location IDs and everything like that, that's just used to do a lookup in your database. Now, what's interesting about the States is that the location is actually encrypted. In, I think, Europe, a lot of countries do not encrypt it, but here it is encrypted. I won't talk about that today, but if you're interested in how that works, I'm going to pimp a talk if you go to look at Black Hat. I think a couple of years ago, I did a talk there about the encryption and how it's used and potentially its weaknesses. So check that out if you're interested in TMC.
Why is traffic encryption, why is traffic congestion encrypted?
Why are the traffic messages encrypted is the question. And I think the answer is just because they can. I mean, it means that generally when people transmit and generate specific equipment to receive it, it just means that then they can control the flow of the information. I mean, nowadays, with information being available in many other forms, you just hop on Google and you get that for free. It doesn't really make much sense anymore. But I think when the system was originally designed, they wanted to ensure that they maintain the integrity and that they could load preset keys into receiving equipment and they would maintain control over the end-to-end. Because I suspect that the companies that were originally in charge of doing this and setting up the infrastructure and transmitting this data, I mean, it might have even been a paid service to begin with, and so you can enforce that using encryption. So they're the general reasons why you would use it. Question up the back.
I think that it's a sold service. XM sells it, and some of the other like GPS navigation units.
Right. So the comment is that it's a sold service. So XM would sell it through their service, and then here maybe the nav systems in the cars, maybe they sell a license to be able to operate in the US, and that way they can enforce that. But yeah, there's been a bit of security research done into it, and as far as crypto schemes go, it's very weak.
One other quick thing to mention too, when you run this, make sure you, in this RDS parser actually, select North America, which I didn't do. That might change some of the output, because the mapping is different and some of the fields are different, and there are some differences between the North American version and the European version. I don't know if that'll change, if we'll see a change in the output here or not, but could make a difference.
And another interesting thing to note just about mono and stereo, do you want to go back to the
Yeah.
is, we were talking about the mono channel, we were talking about the stereo difference channel, so that if you consider with the stereo audio signal, you've got the left component and the right component. If you want to transmit mono, you add them together, right? And you transmit that. But then what information do you transmit so that on the receiver side, you can recreate the left and the right independently? Well, you transmit the stereo difference channel, which is why it's L minus R. So if you were to take your left channel and then just subtract those values, those instantaneous voltage values from the right channel, that's what actually gets transmitted over the audio spectrum. So then at the receiver, you can listen to the mono, or you get the difference channel, and then you simply do a trivial calculation here. So for one channel, you just add mono plus left minus right. And the other channel, you subtract mono and left minus right. And then you recover the left channel and the right channel. And that's how this particular flow graph does it. So it's pretty, pretty simple and ingenious.
Do you want to do the FM?
So we've been talking about FM, and we thought it might be a good idea just to do a very simple sort of flow graph to actually demonstrate visually what FM is and how it works, and just so you can develop your intuitive understanding of what it is and how it affects the signals that you're trying to transmit or modulate. So I'm just thinking the live stream is still seeing your screen. So how do I share this one? That's the question. Let me think about that. What's the quickest and easiest, dirty way to share a screen on a Mac? I think they took it out of sharing, didn't they? Screen sharing. On. BNC viewers. Yes. Okay. Let me just quickly try hooking up this 10, 20, 0, 1, 3, 7. One, two. Never mind. We'll just use the camera because we want to do this quickly and then move on to the next talk. All right, that should be good enough. All right. So what we're going to do here is we're going to use a signal source, which is our simple, basic sine wave coming out here. And then we're going to transition to using the microphone in this laptop as the thing that's originally giving us our input signal, just like, say, a radio station's mic. So it's very simple to do frequency modulation in GNU Radio just by using this frequency mod block. So that takes in a real valued floating point stream and then gives you a complex output that contains complex values that represent the frequency modulated version of your incoming signal. And we've got some scope sinks and FFT sinks to illustrate what the signal looks like in the frequency domain and in the time domain. So if I run this, the first thing we'll see is the input signal in the time and frequency domain. So here I've got a signal source. Obviously here we have the sine wave. And then in the frequency domain, we have this set up. So the F, which is the frequency, is at 1 kilohertz. If I drag the slider, then obviously I'm just going to be changing the frequency of our input sine wave. Now, what you can almost think of, very trivially, is let's say that my carrier frequency is up at 12 kilohertz. If I had this really slow signal coming in to modulate this carrier, what does frequency modulation do? Well, it varies the frequency of your carrier. So if I just move my slider back and forth, say, then it looks like the frequency I'm modulating manually around 12 kilohertz, just really slowly. And so, I mean, essentially I'm doing it, but we can use this block to do that too. And in addition, you can control the amplitude of this sine wave here with amp. So you'll see that as I move this slider, then it's just changing the amplitude of our incoming signal. So this amp slider and F slider just control the frequency and the amplitude of this signal source in there. Remember, I've got the throttle block in here so that we keep the CPU running at a nice rate. And then if we switch over to the second tab, then what are we going to see? We're going to see our frequency modulated signal on a scope sync in the time domain and the frequency domain. But I've done a little bit of a trick here. I've multiplied it by another sine wave so that I can actually center it arbitrarily on the spectrum. So our spectrum here is going to be 48 kilohertz wide because we're in the complex domain now, and my center frequency for the carrier is actually going to be 1 kilohertz. So you can imagine this like the frequency of the radio station that you're going to tune to, like 102.5 or 88.5 megahertz, and then you're multiplying that with your baseband modulated signal that you're going to send out. So let's switch to the second tab here. And things look interesting, a little bit different here. So we've got our 1 kilohertz sine wave being frequency modulated and then being centered at 1 kilohertz. So what I'm going to do is I'm going to turn off my incoming signal and make it DC, right? So now instead of having a sine wave coming in, we've just got a flat DC signal coming in. And you'll see that, why is that out at, oh, you know why? That's what I wanted to do. Okay. I can slow it down a little bit. So remember how we had that sine wave? I've set that sine wave frequency to 0.1 hertz, which means that it's going to do a full revolution in phase every, how long? Is anyone still awake? 10. Right. 1 over f. So, as you can see here, the frequency that we're outputting after this multiply will be centered around 1 kilohertz, but it's going to be varying ever so slowly based upon the level of our input signal. If you look at the input signal, you can see how slowly it's changing. This is voltage, right? So it's changing in voltage very, very slowly. And that voltage is what's controlling the deviation from our center frequency. So to make things easier, I can just make this 0. So now it's going to be changing around 0. And if we make the frequency of our incoming signal 0, then it's just going to stay there, right? Because this thing is just going to be left at one particular voltage level, and that's going to be the frequency that we left it at. Now let's say we make it 1 hertz. So every second it'll be, instead of every 10 seconds, be moving around that center frequency. If we change the amplitude of our incoming signal, what happens? We are now restricting the range of voltage levels that it can go through. See, I can make it really small. And because it's a smaller range, it's only going to move around a smaller deviation. That's how you can control the FM deviation of a signal, basically what range of input voltages it comes through. Also, if we can control parameters downstream, like the amplitude of the carrier that we're putting it on, you'll see in the frequency domain that the amplitude of our final output carrier is also going down, but that only controls the output power essentially of our final product, and you can see that in the time domain as well. And you can see here in the time domain that we have these rapid transitions between different frequencies. So you can see the waves bunch together and pull apart, and that's basically changing frequency as well. And you can see that green is before blue, now green is after blue, and that's when it's ending up on the positive or the negative side, the right hand or the left hand side of our complex spectrum. One interesting thing though is that instead of doing really slow frequencies, if we do something fast like 1 kilohertz, then you get something that looks static because it's moving so quickly and we're only sampling every so often to build up this frequency spectrum. You get these interesting waveforms. And as you change your frequency, you get these interesting patterns start to emerge. And if you're interested, you can look up the functions governing these are called the Bessel functions. Crazy bit of math. But you'll notice here that the center frequency actually changes in amplitude as you change the input frequency. It's not like AM where you have a constant power carrier. It just changes with that. And remember I said that the input signal voltage would change the deviation, so the spreading, the bandwidth of your signal. We can demonstrate that here too. As we increase our input signal's range, then you can see that we actually end up occupying more of the radio spectrum. Now, one thing here is that you have this sensitivity parameter that you can change. I've set that to 1. This sensitivity value internally is simply like a multiplier multiplying the input signal by some factor. So that will also change the deviation or the sensitivity of the modulator. And it's the same effect whether we change this amplitude slider like this or we change the sensitivity slider like this. See, the effect is ultimately the same. So if you have a little HT, a little handy talkie, and you transmit like in a ham mode, you're actually going to be using quite a narrow part of the spectrum because it's designed to transmit within 5 kilohertz or 15 kilohertz or whatever you have. But a radio station like the one we were listening to before with Neil, that will actually occupy a much broader bandwidth because we want to encode all that stuff that we saw in our baseband diagram. So can you show that baseband diagram again?
Yep.
like or not, him, the company, we must hope
yeah, the
that in
demodulator.
this crazy world that we have less
So
friction.
here we had the mono channel, the pilot, the stereo, RDS. We actually have a lot more frequency range that we want to encode because it has all these subcarriers. So you need to pick once you end up applying that to your radio spectrum, your deviation will need to be set right, and depending on the power level you're transmitting at and all sorts of other factors, that'll determine what your modulator sensitivity will be, and then that will end up putting this out onto the radio spectrum. So if you go back to dB baseband, then this is ultimately what is output at the end of the day. So any questions about that? Oh, there's some interesting chatter in IRC about stuff related to IDS. So I think, did you want to mention anything else?
And because of time, we'll skip GQRX, but we can skip
We
that.
can come back to that.
We'll come back next time.
So there's if you've used GQRX, that's a nice package that you can use to actually do all of this narrow band, wide band. It's also integrated with a nice FFT and waterfall. It runs GNU Radio in the background, but it's sort of you want to repeat the question?
Since
No, I mean,
GQRX is on top of out-of-tree modules, or
Well, it's
on top of GNU.
Yeah, it uses GNU Radio. Yep.
So if GQRX uses GNU Radio, can it also use out-of-tree modules, or do they have a different plugin architecture?
Well, I mean, GQRX uses GNU Radio
But just at the core.
just at the core. I mean, I guess if you had another out-of-tree module installed and you had blocks, yeah, you probably could use that, sure.
Okay.
But I think it just uses the core distribution.
cool.
Yeah, yeah.
I mean,
you could do
it's
that.
open source, so you can modify it, but essentially it's a custom bit of software that uses all the GNU Radio horsepower to do its stuff.
Should I run it quickly, or should I?
Let's do it after.
Okay.
All right, so let's shall we go to Shandor then?
Yeah.
All right, so we're going to go to Shandor, who's going to tell us about LT. So we've hopefully given you some cool introductory level stuff that you can play with and get a better understanding of one of the most common signals on our airwaves. Now, Shandor is going to actually do a bit of an expose into one of the other most common digital modulations that appear on our airwaves. It's used by probably everyone's mobile phones in this room, and it can actually convey a tremendous amount of bandwidth, digital data bandwidth, to your devices. So, Shandor, do you want to come down and get your laptop set up? And just before we transition, then let's thank Neil for that interesting dive into FM. And if you have any other question, Neil will be around on IRC as well, and he's a great resource for getting set up with GNU Radio and getting these out-of-tree modules happening. So he'll be around if you want to ask questions. So Shandor, if you don't mind, we're going to put the lapel mic on you.
Yeah, we'll do it over here.
You're going to be on your Mac, right? Yes. Can you log in and call my Hangout so I can share the screen with you?
You share it through Hangout?
Put that on your call in.
Up here?
Yeah, that's fine. Slide that on there.
Please. Microphone check. Can you hear me?
Yes, I can hear the speaker.
Microphone check on? Yep. No, it's good.
Which is the entire band.
Can you send me an invitation for Hangout?
What?
This microphone works in the.
One, two. So John was going to talk to us now about LTE and how we can decode the physical layer.
All right, cool. Say something?
All right, so we're ready. Shandor, please take it away.
Yeah. So good evening, everyone. My name is Shandor Szilvási, and I work at Bastion Networks with Balint. I'm actually with the RF team. And tonight I'm planning to give a little sampler about the LTE physical layer. Balint came up with two separate titles. I think a more appropriate one would be LTE physical layer sampler. Like he mentioned that LTE is incredible and complex. I think it's just incredibly complex. So what you will see tonight is pretty much a sampler. Well, a good analogy would be LTE being a huge rock festival and this presentation being just the very first drink for that. So you drink it and then you can decide whether to dwell into it or whether you decide to return and not go to the party at all. Yeah, there is a hard liquor section of LTE for sure. And we won't go into any of the DSP, the hardcore DSP part of it. So Balint actually asked me last week whether I want to, since I'm coming here to San Francisco, whether I want to give a presentation. And I said, well, yeah, I can give a presentation on the enclosure I just designed. And he said, well, what about LTE? So it's LTE now. But if, in any case, the whole thing becomes boring or, I don't know, I just get stuck, we can always switch to the enclosure design because it's always here. All right. Why do I see? Yeah, so I have a few basic assumptions. I wasn't sure whether I will be able to hit the right abstraction level. Anyways, I will assume that everyone knows what OFDM is and is familiar with the basic modulation schemes, including QPSK and QAM. Just to start somewhere.
Do you want to explain each of them in a small sentence? when you encounter them?
Well, OFDM is a transmission scheme where, well, let me see, I might have, oops. Jeez. That's for later on. I just looked these up because I realized I don't have these in slides. OFDM is a transmission scheme where you can have a pretty spectrum efficient communication with a bunch of subcarriers jammed into a relatively small bandwidth. And it's one type of frequency division multiplexing, which will have I wasn't quite
Sorry,
prepared
did I
for
put
this.
you on the spot?
Yeah, so at the very basic level, you'll have a bunch of subcarriers there, closely spaced. In LTE, those will be spaced like 15 kilohertz apart. And the individual carriers you can modulate using either QPSK, QAM, or whatever. But the great advantage of this is that you can easily accommodate to different channel variations, like using higher order modulation schemes on channels that have larger capacity and just leave out or utilize less the ones that are kind of crappy at the moment. And so one thing to note here is that on the horizontal axis you have frequency where you'll have a bunch of subcarriers. These can be in the order of hundreds in case of LTE, and in the other axis you have time. So if you take a look at it from the top, this will be something that in LTE you call a resource grid, where on one axis you have the frequency and on the other axis you have time, and this will have a pretty huge significance, as you will see in the upcoming slides, if once we can get back there. But before that, just to say a few more words about its complexity, the whole mobile communication network is more than just the air interface. So its backbone and all the network and other entities that are out there are almost as complex as the air interface itself. However, we will only deal with the base station and the cell phone there, which are called eNode B and UE as user equipment in LTE respectively. So from here on, it's only the base station and the phone that we are interested in, because that's where RF happens. And even there, we won't deal with any of the upper layers between the eNode B and the UE. It's just the PHY layer, the very bottom, that is the topic of today's discussion.
Probably some LTE right then.
Yes. So I guess this picture is somewhat familiar because Balint posted it on the website and tweeted it everywhere. I guess now I have more than 3 followers now that I've logged into Twitter after 3 years again. But what you see here is actually Verizon with the downlink at 751 and the uplink channel at 782.5, I believe. So OFDM allows for different multiplexing schemes. This one is frequency division multiplexed, where the downlink has a dedicated channel, which in this case is centered at 751 and is 10 megahertz wide. It has a corresponding uplink channel, which is of the same width. The LTE, the standard itself, supports time division multiplex schemes, but that's less common in the US. That's more like China, where it's more prevalent. But from here on, we'll only focus on the left side, the downlink. So this is what the base station communicates down to your phone. So once you turn on your phone actually has to communicate with the base station. By communication, I mean it has to listen to a lot before it can actually say any word, even just signaling that it's there. And these are the 3 main system informations that it has to acquire first. And the first one is is not officially a system information, but it is the cell ID of the eNode B, the cell tower. And this is a cell ID that's not globally unique, but in a typical area, it's locally unique. So it's not it doesn't have the country code or any of the other components that make the base station unique, but you need to be able to determine the cell ID to be able to decode the master information block and the system information block later on. The cell ID consists of two parts. One is the group ID, which is NID1 in other names, and that can take values from 0 to 168, and NID2 is just from 0 to 3. Oftentimes, if the base station is set up with 3 sectors, NID2 usually, the 0 value of NID2 usually points to north, and then the other ones are assigned around. It's not in the standard or anything, but it's usually something that's being followed. But the two IDs together give you the cell ID, and you will actually need that to be able to decode the master information block. One important thing here is that none of these steps use any of the super DSP intensive diversity schemes or MIMO schemes of LTE. So you can use, in order to acquire the cell ID, MIB, and even SIB, you can get away with a single antenna. And when you LTE is pretty flexible in terms of frequency allocation, so that the providers can utilize it in various scenarios, whether they acquired like a 5 megahertz wide band somewhere or a 10 megahertz wide, they want to have take the most out of it. But when you turn your phone on, you don't actually know how wide a particular band is. And at the very beginning, you can always assume that it's the smallest one, which is like 1.92 megahertz wide. And all the information that's needed to be able to figure out how wide the actual band is included in the actual LTE band is, and it can start processing that full bandwidth carries the system information block. These are numbered from 1 up till around 16 right now. It's SIB 2 and 3 that carries information about which provider that actual eNode B belongs to. But again, for doing this, you will have to process the entire bandwidth, let it be 5, 10, or 20 megahertz. Getting the MIB is something that's, again, transmitted in the center of 1.92 megahertz. So if you have an RTL SDR, this is probably where your decoding capabilities will stop.
Can I ask a question, Chandra?
Yeah, and
where does the LTE hard liquor start in this diagram?
I would say right here, when you have, this acronym stands for well, let's go through at least the basic ones. So this is the broadcast channel. P always stands for the physical one and is usually the bottommost layer. This is just broadcast channel, and I forgot what BCCH is, but that's the logical counterpart of the control channel, broadcast channel. This is the shared channel, and processing this is what requires processing the entire bandwidth, doing decent equalization, and even though for processing the SIB, it's only transmit diversity that's being used, that's the channel where the actual data content comes down when you play a YouTube video or download a large blob over the internet. And
Can I attempt to say this in my own words and have you tell me I'm completely wrong? Okay.
And again, I would prefer to make this a conversation as opposed to me presenting something.
Great. So it sounds like the phone starts up and listens in kind of like a wideband spectrum, right? And it's looking for some really specific, simple information. And in that simple information is the channel ID groups, right? To try to determine which physical cell it's in. And then it's going to try to pull the MIB out of that. And from that, you can continue, like, it's almost like a handshake. So you're kind of working into your levels of complexity up, right?
Yes.
Okay.
So actually, let's move forward to here. If you look at that website there, I think that's going to be a very useful resource for this discussion in general. Do you remember when I mentioned that in one dimension you have frequency, the other one you have time? So this is actually one resource block spanning the entire width in frequency of the LT channel on the vertical axis and its time on the horizontal axis. And once everyone has this on the screen or can bring it up, I'd like to go a little bit further. The previous diagram is actually what's in this dashed section here. This is slightly exaggerated. It's way much narrower than it looks on this figure. But this is the center of 1.92 megahertz, which is 12 resource blocks. One resource block means 12 subcarriers in the LTE lingo. So this is 6 times 12, that is 72 subcarriers, and it's one frame long. Well, one frame length is actually 10 milliseconds. And what you've seen in the previous slide is actually one whole frame. One frame comprises 10 subframes. A subframe can be called 2 slots, and within each slot you will have, in case of normal prefix and FDD, 7 symbols. So again, from here on, we will only focus on this section. Well, one chunk that's like one frame long. And we will just bisect this diagram because this is pretty much what's absolutely central to LTE. And the way we will do it, we will perform synchronization and again process the physical broadcast channel to gain the MIB. And the MIB is actually roughly 20 bits, but it's super protected, so it has lots of redundancy built in the way it's being transmitted from the base station. So it's actually the same content is being transmitted for 4 frames, in 4 frames. It's only, so all of these mean one frame, and one frame comprises 10 subframes, and the MIB is actually being transmitted here in this purple block. But in order to be able to decode what's in the purple block, you'll have to use these signals, the primary synchronization signal with PSS and the secondary synchronization signal. So soon there will be a demo, I guess. Again, here, if you bring up the website that's here, you actually have a legend there that will tell you which signal is which. But again, what we'll attempt to do is to capture some signal, then we'll try to find what's marked purple here. This is the primary synchronization signal. And what you have to know about the primary synchronization signal is that there is 3 of them. These are so-called Zadov-Chu sequences, which have pretty nice correlation properties. So what you usually do is you just tune to the center where you assume that the LT band center is, and you correlate against all 3 of these signals, and you just try to find the strongest correlation peak of the 3. And you pick the strongest one, and you say, okay, this is my cell NID2. Yep.
A bike might have moved for those listening out there in internet land.
And after that, you will follow a similar scheme for the secondary synchronization signal, which is this light blue signal. But for the secondary synchronization signal, there are actually 167 signals, and you don't usually want to have 167 correlators running in a way. And you also need the information of the from the NID2 value. So while you usually use, well, it's pretty easy to use a time domain correlation for just grabbing the PSS. For the SSS, it's usually performed in the frequency domain. You just capture it, and you just compare it to the sequences one by one. And with that, let's jump into the demo, which I really hope I won't screw up. After all, it's a demo. Can I move this over here?
So did it take a PhD for you to learn all of this?
No, I just started learning it. It has nothing to do with that. Well, now that you've mentioned it, just for a small detour, throughout my, where is this cursor? Actually, throughout my PhD, I had an opportunity to build this SDR for my research, which was, well, it's on GitHub and open source hardware and whatnot. It's a simple modular SDR with a power management module, FPGA, a flash-based FPGA SoC in the center, and a replaceable front end. And well, actually, it worked out pretty well there. So,
Shandor, is it possible to increase the font size?
in MATLAB, you think I can do that? Let's see. Fonts, maybe. Okay, first I just run it on a pre-recorded file. I recorded it 5 minutes ago, and then we can try recording something again once I can find my cursor. All right. So this one I actually recorded at 7:31, and I believe this is AT&T, but I would have to look it up. There are databases where you can check these. What you have to see here is that this is actually not that wide. It's a 5 megahertz wide band. Well, 5 megahertz from, yeah, that looks right. Roughly 5 megahertz from here to here. So again, time is horizontal and frequency is in the other direction. And this is just the absolute value of the incoming signal. And again, this is 5 megahertz, but for MIB, you only need to process the central 1.92 megahertz. And now you can't really see what's going on here, or whether it's distinct from the other one, because the downlink channel is usually like 90% filled. It's like as if everyone would download everything. There is traffic here, even if no one is downloading anything, like just transmitting the reference signals so that the phones still have the capability to equalize their channels and stay connected to the network. There is always traffic on the downlink channel. As opposed to this, the uplink channel is is oftentimes like a barren, deserted area, like with utilization below 5% or so. So I don't know, when the first time we were trying to do a capture, I actually had to ask a colleague of mine to upload something that's like 100 megabytes just to be able to find something there. All right. Well, what's going on? Oops. Yeah. These. You know what? Let's try to get the other one here. Okay. So again, this was 5 megahertz wide. This is the center of 1.92, and that's the actual center of 1.92 after filtering and downsampling. So if you have an RTL SDR, I think, what's the maximum sample rate there? Is it like 3.2? So that's sufficient to be able to decode the central part.
And in a future episode of Cyberspectrum, Neil might actually use LTE cell scanner to do exactly that.
Yep. So what's the next step? We need to get the NID2, and that comes from the primary synchronization signal. And again, there are 3 different primary synchronization signals you want to correlate against. And this is what the correlation against those 3 look like. And it looked nice on the screen. It's not that great here, but maybe make it even thicker. You can see that with PSS2, I can read it here. I'm not sure who else can read it. You get these nice peaks, and these are roughly, well, these should be roughly 5 milliseconds apart, but it's usually the case that only like the 10 millisecond one, at least 10 millisecond, with 10 millisecond periodicity, you get these nice peaks. It's not always this nice. If there are multiple base stations transmitting at the same time, then you might get peaks for the other PSSs, and that's actually something that's an information when you want to switch to base stations. This helps you determine, okay, I can see a base station with a cell ID that's reasonably strong, so if something goes wrong with the one I'm connected to, then this might be one way. Of course, there are higher level mechanisms where the base station actually tells you, okay, connect to this base station instead of that, but this is another good indicator as for how many base stations are around there and which one you might be able to communicate with. So once you have the PSS, you do the same thing for the secondary synchronization signal, and the 2 things together should give you the cell ID, and okay, excuse my it's nice that I print these things here, at least I don't forget them. So it's once you correlate with the PSS, it's not just that you know which PSS what the PSS value is, but the position of these peaks in time will actually tell you where the frames start. So this will be a pretty good reference for you if you want to do time synchronization. So once you have this, you do the same thing with the secondary synchronization signal. You can, well, yeah, I keep running ahead of myself, sorry. Also with the PSS, you can use that to do frequency offset estimation and use that for compensation. There are other ways you can do, or other popular methods to do frequency offset detection. You can rely on the cyclic prefix, which is sort of an OFDM related paradigm. But again, the important thing is that from the PSS, you get the NID2. From the SSS, you also pick the largest correlation peak, and that gives you NID1. You multiply it by 3, add this guy to it, and then you call it the cell ID. So once you have the cell ID and you know the frame timing offset, you can actually take my cursor back. That's horizontals.
I think we're seeing some advanced MATLAB here.
Yeah, well, okay, I got back to another recording that I took in our office. There it looks super nice where these things are mapped or laid out in the spectrum. Again, if there is other traffic, then those PSS and SSS signals are surrounded with actual downlink traffic. And you just see this whole mess of data or spectrum being utilized. But in general,
Actually, that's
Can I just ask you something about something interesting I noticed? Can you just zoom out just one? No. Can you go back there? Back there, and then if you'll notice, you got these highlighted portions which relate back to start of the frame, right?
yes. So this.
But here, if you look in the actual spectrum, you can see an interesting pattern forming there. I mean, that is directly correlated with that, right?
Yes.
So they increase the power on those symbols.
Well, that can be a technique that the synchronization signals can be boosted compared to the other generic downlink traffic, just so that the phones have an easier time to keep the synchronization with the base station. So there are lots of other types of synchronization signals built into this whole, I would say chessboard, but it looks like, I don't know, just random C from above. Yeah. Again, you know what? Let's restart it with the other waveform because. Oops. 1 second.
how precise does that synchronization need to be?
How precise does that synchronization pulse need to be in between each other?
So in frequency, the subcarriers are spaced 15 kilohertz apart, and you want to be pretty precise with the frequency synchronization. And if you go to that website I just showed you, that will tell you how much, with the different configurations, how much signaling overhead you have. Usually, like, it can be up to 20-25% of the whole area that's devoted to control and synchronization and not actual data. Maybe if I bring, there you go. So what synchronization signal here? This is PSS, the purple one. The yellow is SSS. And you know what? Let's come here. And just to get a view of the whole thing, this is a 10 megahertz wideband, which is 50 resource blocks. This is how wide it is in frequency, and this is the central 1.9 megahertz we were talking about. These red and gray dots, those are all synchronization signals spread out both in time and frequency so that you can get a feel for what the whole surface looks like so that you can equalize it out before doing the OFDM demodulation.
When you were showing the correlation peaks for the PSS, those were the Z-off-2 sequence, the cross-correlation peaks?
Yes, so the absolute value of the cross-correlation with the Z-off-2, with the three distinct Z-off-2 sequences.
Right, okay, thank you.
And for some reason, I'm showing the same thing, so. All right. So this is something from the office. Well, the energy, partly because of those chess-like patterns for the synchronization signal, you can still see this whole column to be highlighted in yellow. But if you look closer, now these chunks here are more prevalent. And these are the sections where the PSS, SSS, and the actual broadcast channel content are being brought down. So this is, again, the central 1.92.
Chandra, while you zoom in, there's been a question from the internet. Does the MATLAB script live online? Is it available online?
It uses the RT system toolbox, which is not an open source tool, so I'm not sure if one could use it if it was available online.
But you're going to offer some open source alternatives and toolkits that actually do a lot of LTE.
Yes, I have a slide on that,
Yep.
like what options there are. All right.
Hi, this is really cool. I've been lurking in the back, but but yeah, now I've come forward. I'm kind of like half paying attention, so I'm probably missing some things.
Yep.
But you were talking about the synchronization frequencies, and are the synchronization frequencies dynamic, or are they fixed at a certain frequency? Because it sounds like there's lots of frequency multiplexing. You're kind of jumping between them. Is that rational in any way whatsoever?
So you roughly know where these LTE bands are because that's well documented, and you know where the operators operate. You tune closely to that frequency, and then you use, for example, the PSS to do a carrier frequency offset compensation. So you are logged into the center of that whole band. And those other signals, so you don't process those channels separately. You process the entire channel at once. So it's not like you have separate carrier frequencies or you tune here and there. You tune to the center, and that's part of how OFDM works. You process the entire channel at once, like one symbol time and the entire width in one step.
We've got another question from the internet too. General LT question. When a device's receive signal strength indicator, RX signal strength indicator, shows a weaker signal, data speed often decreases. Is this because of bit errors, a lower percentage of data bits compared to overhead, or some other cause? Basically, how do you measure RISI? How do phones report the bars? How is that computation done? Is it just from bit errors, or is it from some lower level assessment of the size?
As far as I know, there are multiple ways. Seems like I'm still online.
No, you're good.
Yeah, so this is, you can actually derive one kind of RISI from the synchronization signals. There are other ways you can measure RISI. I'm not sure what the details of that are.
Well, this guy was asking about it in terms of bit error rate. So once you actually, once you do the decode, you can get stats from, the turbo, how many bits it's correcting, all that sort of stuff. So there are a number of different layers from which you can derive your signal strength or your signal quality.
Yeah, so one reason for having that many synchronization signals is that the phone can make measurements continuously, and reporting it back to the base station, telling it which channels I see crappy from you. So the base station in the next round will allocate the part of the spectrum to that UE that's actually in good condition between the two, and just leave out the ones that are crappy.
Yeah, so the system is essentially closed loop, so that it's allocating resource blocks that have a good path between the antenna and the mobile phone.
Yes.
So it's actually pretty smart.
All right, I think it's a little bit more prevalent here. The red one, which is from here, roughly to here, is the primary synchronization signal. And I guess the way I created the bottom plot, it might be shifted like just slightly compared to the other one. But before that is the secondary synchronization signal, and this purple block is what we are interested in. Again, in the central 1.92 megahertz, this is the region of the resource grid that contains the physical broadcast channel. And even though that still spans a pretty reasonable amount of resource blocks in that whole resource grid, this is all the data it contained. And from here, the first 3 bits will tell you how wide the actual LTE band is. 50 corresponds to 10 megahertz. This is 50 resource blocks. That corresponds to a 10 megahertz wide LTE band. If you see 100 here, that's the 20 megahertz wide LTE band. And there are like 3 more quasi-standardized bandwidths, 5, 3.5, and 1.92. And another interesting, there are some information here that's related to the hybrid to HARC, the hybrid automatic request mechanism. And the very end, I believe, is part of the system frame number. This is actually incremented in every frame. And it's a 10-bit number, so it wraps around at 1024. But one interesting thing here is that they try to save some space, so it's only the upper 8 bits that are included here, and the rest of it you actually have to figure out how the PSS and the SSS are positioned. But basically, once you have the MIB, you know that, okay, even though I've processed only a 1.92 megahertz wide band, now I know that the whole thing is actually 10 megahertz wide. So now I can start processing those synchronization signals, equalize the channel, and start decoding the actual shared channel. And the first thing you would grab from the shared channel is the system information block, which will tell you whether the base station belongs to Verizon or T-Mobile, whether you are allowed to actually talk to that base station. And there is like a zillion other parameters that you have to acquire first, like the different capabilities of the base station before you can actually signal that, hey, I'm here, please give me an ID, and then later on establish a connection at the file layer and upper from there. And I think there are 2 interesting aspects here. One is that you can indeed process this part and even the SIB if you can make a capture that wide with a single antenna. And the other thing is that none of these things are encrypted or protected in these kind of means. And as some closing notes. Again, I really like this website, even though it has a few minor bugs. There are quite a few open source projects. I only mentioned here the most well-known ones, and why not to start at the very bottom. LTI is actually an MIT project, and it's MATLAB/Octave code. It's MATLAB code, but it's written in a way that you can run, I believe, the whole thing in Octave, and that might be a good start if you want to experiment with things, because it's probably easy to visualize things in an Octave environment than jumping into the C or C++ code. GRLT, well, that's in GNU Radio, so that might be another good starting point. LT cell scanner is mainly for grabbing the MIB, and I believe it was mainly targeted at the RTL SDR. So that's definitely something that you can start playing with if you have an RTL SDR. SRSLT is written in C. One interesting aspect of it is that it also uses the LT system toolbox as test benches. So if you find some MATLAB code there and you're unable to run those various functions, that's probably because it has a huge dependency on a MATLAB toolbox that's not included in the repo. OpenLT is a C++ project. I think their source code is pretty readable, and they structured it following the actual standard very closely. So if you want to understand or just map the actual standard, which is quite readable, then this could be a good starting point again. The way I mentioned that it's readable is because earlier cellular protocols, like the ones for UMTS and whatever there was before, were pretty painful to read. And compared to that, the LT standard is reasonably well polished. And open interface is just another option. So some other resources. The first two are the most relevant parts of the standard. Those are freely available. If you just Google them, it will come up pretty quickly. I really like this book. Like, if you just keep it on your night desk and start reading it, it's good. Sometimes it will make you fall asleep pretty quickly, but it's readable. It has super nice figures, and yeah, I highly recommend that. So MATLAB LT System Toolbox is actually a non-open source product and is priced somewhat high, but I believe that their documentation here is freely available. You don't have to have a MATLAB account to read it, and that I can highly recommend as a starting resource. Whether you like MATLAB or not, their documentation in general is pretty good, and for the various sections, even here, they have good references. So if you just want to delve into a topic within LT, you look up their website that gives you a nice overview, and if you want to read more, you just follow the different references at the very bottom of that page. This page is for playing around with the LT resources, and is the one that we just saw. Cell Mapper will give you a Google Map view with the various cell towers and their corresponding IDs. So if you just want to look around what's in the neighborhood, that might be a good starting point. And this one is for identifying what frequency bands correspond to what cellular band. Like if you want to check what's at 731, you just type that frequency in there, and it will tell you what its corresponding LTE name is. And I believe that's it. Yeah, if anyone wants to talk about this, I guess that's going to happen.
Tell us a little bit about it.
Yeah, no, that's going to happen next time. Are you kidding?
No, just quickly.
Yeah, someone ordered a B200 Mini in the office, and no one started to use it. So it was just sitting on one of the desks, and well, I started drawing up this enclosure on the weekend, and then started refining it, and again, this could be another talk. But there is one tool I can, if anyone is interested in doing 3D printing and this kind of maker movement, Fusion 360 is a product from Autodesk, and well, this whole thing is turning into an advertisement. But it's actually free for hobbyists and for startups with no income or for their first 2 years. And it's super capable, and their UI is really good. It's not painful enough so that I would stop using it with a touchpad. So I guess if you really want to, and they have, well, I should basically just stop here. This is the actual B200 Mini there.
Did they have tools for importing the PCB artwork into this, or did you have to manually do it?
This one I did manually. You can import a bunch of stuff, like this is like a McMaster car component, and they actually have the 3D models there.
Yeah,
so
McMaster's pretty awesome.
yeah, so you can import STL, IGS, and other kind of formats. There might be a way to export PCBs. I haven't experimented with that. Anyways, this is pretty much what I've prepared for today. If anyone has further questions, please shoot them.
Any other questions for Shandor before we close out? No? Okay. There was one comment here where we were talking about RISIs and lower power levels resulting in higher BER, which results in more retry attempts if the FEC can't correct it, which lowers the data rate inherently when trying to transfer information. Does that make sense to you? If you've got bad channel conditions, if you're further away from the base station or what have you, and you're pushing your power limits, and that's resulting in a higher BER because your FEC can't correct it, that would lower your possible data rate. And I mean, what would happen then? The base stations would pick a lower modulation coding scheme to help you still transfer data?
Yes, so that's adaptively adjusted
Okay.
to the channel conditions.
So the modulation coding scheme you often see abbreviated as MCS, and there's a number associated with that maps directly to a particular kind of modulation scheme and what level of forward error correction there is on there. Oh, there you go.
Yeah. So even for the UEs, for the phones, there are different categories defined in the different releases. And I think these numbers can be pretty staggering. But here are, so the modulation schemes supported are QPSK, QAM, and QAM can go up to 64 in the most recent or most capable phones. Again, it's not just that you have an LTE phone, your phone usually has a category associated with it, which will tell you how much, what peak data rate you can achieve with it. But yes, so if the channel conditions are pretty bad, then this will potentially drop down to a lower QAM or even QPSK.
So that's saying 3 gigabits per second for MCS 8? Is that right?
Yes.
That is insanely fast.
That's spread across all phones, right?
So,
Well, I guess it's 3 gigabits a second.
That's the total bandwidth of all results.
yeah, that potentially has some assumptions that your phone won't satisfy. So this might require 4 antennas on the UE or even more. So that's like a theoretical bandwidth if you support everything that's maxed out in and is presented in that standard.
But it's also on carrier, so multiple handsets can get that throughput, right? If you had 5 phones all operating at optimal.
So I think this, well, I have to check where this slide comes from. It's just a backup slide for me. But so there are multiple things. I think this is defined between a single handset and the base station. So it's not an aggregate in this sense that it's measured between the base station and multiple UEs. But one thing that's started at LTE release 10, and that's the point where LTE was started to be considered 4G, and it's called carrier aggregation. So I showed you one LTE band, which was like 5 megahertz wide. There was another that's 10. And maybe the same operator can have a 20 megahertz wideband at 1.9 gig or so. And carrier aggregation allows you to use these simultaneously. So it's not just that you do OFDM. Well, in the uplink, it's actually single carrier FDMA. But it's not just you use a single LTE band for uploading or downloading things, but you can actually aggregate those and thereby extend your overall bandwidth. And this, well, everything up from release 10 heavily relies on carrier aggregation to achieve these numbers.
Okay. Any other questions? Looks like we've satisfied everyone's curiosity for the moment. So let's thank Shandor in a big round of applause. And especially because I asked him on relatively short notice and is having a nice visit to San Francisco this week from Atlanta. So he was very kind and amenable to giving up his time tonight. So let's have one more round of applause for Neil for taking us through the tutorial, and then for Shandor as well. Okay. So thank you. I'm going to hand the mic over to Neil, and maybe you can tell us a little bit about what's coming up. No, just to close out.
Yeah, so the next Cyberspectrum meetup will be in 2 weeks here at Noisebridge on July 13. Today, right now, it's already 10 o'clock, so we'll probably wrap it up for today. We won't get to the install fest slash questions, answers, hands-on. So we'll do that maybe tentatively next time in 2 weeks. So if you have questions or you want to set up your environment or just kind of an open house, install fest type of thing, bring your equipment, bring your laptop, and we'll do that tentatively in 2 weeks, and use one of the speaker slots for that. And then after that, after July, we'll have a couple of meetups in August and September, which might be in other locations. Details are forthcoming. We have to confirm that we can actually get the space and the time that we want, and once we do, we'll make an announcement. It's pretty exciting, pretty cool stuff. And then in October, we'll be back in South Bay. October, we'll be back in Santa Clara, and then we'll keep going back and forth. November, we'll be back up here. So just stay tuned. We'll keep the site up to date and keep it updated, and give everyone some advance notice as to what's cooking. If you have any questions, just contact me or Ballant, and we'll see you next time. Thanks for coming. Any other announcements? I think that's everything. Okay, have a good evening. Thank you, everybody.